All right, today is the day we're going to put together everything we've learned so far, and we're going to talk about, given some data, how do we choose the best and most appropriate model given our options that we've worked with throughout this chapter. So if you missed today, the activity is something that can't really be replicated on a video, but there is something we're going to talk about on this front side. So here's what happened. They had some pullback cars, and what they did was collected their own data using pulling back the car at distance of 2 inches, 4 inches, 6 inches, and 8 inches. Okay, and each group completed this and calculated regression models with their own data. So in practice, that meant each group could have a different most appropriate model. So the job was to analyze each type of regression model. So the options that were given here were linear, quadratic, exponential, and I went ahead and had them do the power regression as well, just so we could get used to the options that we've been working with. And things that they can use to decide the best model is R, the correlation coefficient, but that's only if we're comparing different lines of best fit, or we're looking at only if a linear model is appropriate. Remember, that's looking if R is close to 1 or -1. You could look at the actual scatter plot, seeing if the points are relatively straight or more curved. Then specifically, once you actually calculate your different models, putting that equation on the graph and seeing how closely the curve or the line fits the actual point. And then the last one we talked about last class was residuals, comparing the error values for each model. Of course, we're looking to minimize that error, so it's the error that would be the smallest for each model. And another thing we want to look at when we're comparing different models is trying to see if the residuals roughly alternate. We want about the same amount of positive values as negative, and in a perfect world, they would alternate back and forth, positive, negative, meaning when we were having our scatter plot, we had 1 point above the curve, then 1 below, then 1 above, and so on, all the way through. In practice, that doesn't happen perfectly every time, but we do want them to alternate every few. Okay, so the choice selection was definitely dependent on the actual model that they were working with based on their data. So what we're going to do is kind of practice these same decisions on the check for understanding on the back side. Okay, so if you flip it over, we're given a situation here where we have water at room temperature. So in this case, it was 21.3 degrees Celsius, and they poured this water into an ice cube tray. Then they put that tray into the freezer. So the temperature of the water was measured every 5 minutes after that. So it started out at that 21.3, and we know if we put water in a freezer, it is going to cool down over time, so they measured that time. What I'm going to have you do is answer these questions based on what we've done this chapter, and then once you've done that, you can come back to the video, and we're going to talk about something new. Okay? So hopefully you had these values. Now, something that I mentioned briefly is anytime you're given a situation, you want to pay attention to any details they give you. We've seen this with time for sure, is they sometimes give you the variables that they want you to use rather than X and Y. So in this case, they gave you T and M that you needed to use in your equation. So check out for that. I did not tell you what to round to, so I don't care how many decimal places you had, but you did want to make sure you put approximately. And for correlation coefficient, I always want you to use 4 places. Okay? So hopefully you said linear was appropriate because the R value is close to -1. But what I want to talk for a second is how we choose the best model, not necessarily something that's appropriate or something that's good, something that works, but is this the absolute best for our situation? So we're going to go back to the context first, and then we'll come back to some of these items here. So based on the context, if you look at the table, it is organized, and linear would indicate that each of these values would be changing by relatively the same amount. And at first it looks like we're somewhere between 1 and 2 degrees away each time. So it's not bad in terms of linear, because perfectly linear does not happen in practice. Okay, but if we think about the water being frozen, this is something that is a theory-based situation, because when we talk about water freezing, water has a freezing point based on theory, and in this case it's Celsius. Okay, so the freezing point for Celsius is 0 degrees. So this is not going to continue forever, lower and lower and lower. It's going to level off once it hits that freezing value. Similar to like we talked about with Newton's law or Boyle's law with the pressure. Okay, we have some situations that are supposed to look like this every single time. And when it levels off, specifically, this is theory-based exponential model. The other example we had was half-life that was exponential, another theory-based model. So while this was a very, very good model with linear, another thing we're going to do is look at what's called the coefficient of determination. So R is for linear, but this R squared, this coefficient of determination, we can do that for every type of model. And that makes it a little bit more useful for us. Okay. We already went over scatter plots and residuals, kind of the things to look for. Go ahead and add those to your notes here so that you remember what we're kind of doing for these next few. Okay, so this one, it says R squared measures the percent of variability in the response variable that's accounted for by the least squares regression. Okay, so that is not exactly super user-friendly in terms of going from math language to what it actually means in English. So we're first going to get the R squared value from up here, but then we'll kind of say what this means in context. So make it a little bit more clear. So one thing that does matter, it is measuring a percent. So we're always going to change this to a percent value. So if I move my decimal 2 places from here, that's about 99.37%. Okay, and what it says is my model, in this case it was the least squares regression line or the line of best fit, but you're going to say whatever model you're working with. So the line of best fit. Okay, and it accounts for or takes care of this percent. Of the variability. And remember that variability just means the difference from like what is supposed to happen and what actually happened. So the variability in the response variable just means the y context. So for us, the y context was talking about the temperature. Okay, so when you're interpreting this in context, the things that you're going to really put in here is whatever model that you're working with. So it could have been you could say linear model, exponential model, quadratic model, and so on. But it's accounting for whatever your R squared value is, and it's the variability in whatever your y context is. So it's basically giving you a measurement of accuracy. Okay. Another thing we're going to do is look at the residuals, but instead of listing them, we're going to graph them to compare them, because when we're dealing with a small set, it's really easy to look at the list in our calculator figure out their relative size, and if they're relatively alternating. However, our data set is not always small, and it's not always in order. And so to account for that, we're going to graph instead. Okay, now it's not going to tell us about our size too much, but it will tell us about the shape. And I'll talk to you about how we can use that shape to compare. So first off, I went ahead and pasted here the instructions, but I gave you a note card that has these instructions on there. We've practiced a lot. First thing we need to do is go calculate the residuals in our calculator. So in our list, remember from last time, you're going to go up to list 3, and then you already calculated the linear regression, so all you have to do is second step, residuals. If you ever get an error here, it's because your calculator has forgotten the line of best fit, and you just have to repeat steps 1 and 2 to calculate that regression model. Okay, so there are my residuals. Again, this was in order, and it's small. So from here, I can see that those are relatively small, meaning relative to these degrees, this residual is a very small percentage of 21, okay? But we also look at alternating and what positive, negative, positive. Not super great alternation. They do balance in size, though. We've got 3 that are positive and 4 that are negative, so that's relatively equal sizes of amount of positives versus negatives, but we're going to graph them. So here's how this works. It says we're going to turn the plots on and edit the type to scatter plot. Well, we've already done that. We just want to make sure that it says list 1 and list 3 instead of our list 1 and list 2. So second y equals, go to your table here and change this to second list 3. And the last thing is zoom 9. Now again, this is going to show the shape. It's not going to show the relative size if we're zooming in. Okay, so zoom 9. And I just want you to sketch these roughly. I do not want you to worry about the label for this, but you should know kind of what you're graphing here. We are saying that for this first one, and this is not required, but I am going to show you on here just so you're clear on what's going on. This is on my y-axis, the residual value. And then on my x-axis, this is still my time in minutes. So this is my residual for my original starting time, my 5 minutes, my 10, my 15, 20, 25, and 30 from the original table. So first 2 were above, all the ones in the middle we had below, and then this also one. Now, we are going to compare this. When we do this, we're going to just mention the shape, and then we will overall talk about which one's best at the end. Okay, so this one, we've got residuals, make a U shape, or you can say residuals are shaped like a parabola, and that's not ideal. That doesn't mean the model was bad. In fact, we decided that it was a good model based on R. It just means it's not the best model. Okay? So what we're going to do is compare a couple other ones. We've already decided that this really is a theory-based exponential model, but they're not always going to be that way. They might be impressionistic models where they may be exponential in this case, but there's no real reason behind it. So we're going to test some other ones today. So first thing is the quadratic model. So I'm actually going to let you, and I'll catch up here, but I'll let you go ahead and calculate the quadratic model and write down R squared. You can pause the video while you do that. And I do not want you to do the exponential until after this, because remember with our steps here, we're going to have to make sure that we graph it before we move on to the next one. Okay, so pause the video and take care of that. Okay, so here's the model. Hopefully you remember to use T and M, and the R squared was 99.99. Okay, so I'm going to go ahead and, just like we did last time, go ahead and paste the residuals into a different list here. So second list into residuals. That way we can see them side by side with the previous one. Okay, so for these ones, we've got a little bit more alteration. So that's some good news. And if you notice, also, these values have an extra 0 in front, quite a few of them. So they're smaller than the others. Okay, so I'm looking at them side by side because from our graph, when we hit zoom 9, we're not going to be able to determine its size. Okay, so from the graph, if you go second y equals, I'm going to change this now to list 4, second L4. And just to show you, if I hit graph on this one, do you see how they're way smaller? The reason I'm going to have you hit zoom 9 every time is because there's no guarantee that you start with the worst one and are working your way to the best one. So if you don't hit zoom 9 and the model you're working with is actually worse than the last one, you might be missing some of the residuals. Okay, so hitting zoom 9, we can plot these ones. Okay, you don't have to take a lot of time again on this. We're just using it to describe the shape of the residuals themselves. Okay, so on this one, they're alternating quite a bit better than the last one. So these ones have residuals that cycle around 0. And remember, 0 is good because that means literally 0 error. So I'm cycling above and below 0 when I go from positive to negative. Okay, I'll have you pause the video and go do the exponential model for me. All right, so exponential model looks like that with an r squared that rounded to 100 if you use 2 decimal places after moving the decimal. After that, if you wanted to add the extra decimal, because you never want, when you're comparing 2 different functions, for them to round the same. That doesn't really tell you anything about which one does better without looking at your graphs or another one of our methods for choosing an appropriate model. So add a decimal place, or it does round technically higher than the last one. And then looking at the residuals in the table, again, this is a very small set and it's organized. They're alternating well, just like the last one. They are small, lots of zeros in front like the last one, and they are a little bit smaller than the previous one. Okay, so I'm going to change that second y equals to list 5. And then hit graph. Do you see how they're a little bit closer? Now you would have hit zoom 9 because there's no guarantee for order. And from that, the shape looks almost identical to the previous one. So that's why the shape of the residuals isn't going to be good enough necessarily on its own. Okay, but it is a powerful tool for us to use to deal with kind of these comparisons. Let me get back to that. And we'll describe its shape as well. Residuals, cycle around 0. So we're supposed to pick the best model based on the residual plots and r squared. Okay, we already talked from theory that this is exponential, but the other 2 factors did support that. Okay, so the exponential model is most appropriate since its residuals cycled the closest around 0. Additionally, its r squared value was the highest. Okay, when I have you sketch these out, I will always have you describe the shape next to it. Okay, so that's something that not only did I have you write it here for the notes, that's something that I want you to do when you are doing your homework and when you're taking the test. Okay, another thing that's going to be important is that you are using the word residuals here. It's important to me that you recognize that this is not the original scatter plot. This is the graph of the residuals. We're not saying that the exponential model cycled around 0. We're saying its residuals are, or the error points would do that. Okay, so that word residual has to be included here. When I ask you to describe which one's most appropriate, you don't have to mention all three because you wrote about all three on your graph up earlier. Okay, if I asked you to compare though, then I would want you to mention all of them in your sentence here. Okay, I'm going to do one more thing before I wrap up here, is just as a reminder of what this r squared stands for. Okay, when I say its r squared value was the highest, what I'm saying is the coefficient of determination said that almost 100% of the variation in temperature was accounted for with the exponential model. Okay, the linear model was really, really good, but this one was best.